Everybody, today we're going to be talking about one-sided limits. This is part 3 of our video series on limits of functions. Now, if you've seen our other videos, you've seen this function before. This is a piecewise function, which is the line x plus 1 as long as x is not equal to 1. That's this right here, everywhere except for this little dot. And when x equals 1, the value of the function is 3. That's this floating dot right here. So it's basically a line with a little hole cut out at x equals 1 and a dot right above it. That's what the graph of this piecewise function looks like. Now, if you remember, we talked about limits of functions. Specifically for this function, we talked about the limit as x approaches 1 of f of x. And I said, let's imagine that we're walking along this line toward x equals 1, and we're looking at our y values. We decided that the limit as x approaches 1 of f of x is what the y values are approaching, which would be 2. And I denoted that with just a little arrow here. I'll draw it again. Imagine walking along this line toward x equals 1. My y values are approaching 2. We also said, well, why can't I walk along the other side of the line, starting at values of x above 1 and decreasing? That would give me something like this. And we determined, well, the y values are going to approach 2 in the same way as it was on the left-hand side. Now in math, each of these approaches is considered a different limit, and they're considered one-sided limits. Okay, so let's look at this blue limit first. We say that if we approach f of x as x gets close to 1 from the left, we denote that as limit. X approaches 1. We put a little minus sign, meaning we're actually less than 1 as we approach 1. Using that reason we used before, this limit is actually going to be equal to 2. So the notation is almost the same. We just have this little minus sign which says that, okay, we're on the lower side of 1. We're less than 1 as we approach x equals 1. What about this orange limit? We write that as limit x approaches 1 from the right, f of x equals, well, we reasoned that out before. It's still the same. Our y values are getting close to 2 from the right-hand side, so we write that this one-sided limit is equal to 2. Now before, we didn't have these minuses and plus signs, right? We didn't have a one-sided limit. We just had, well, what you would call, now we would call it a double-sided limit or just the regular limit, right? I didn't put anything next to the 1. What does this actually mean now? So here's a key point, right? In math, this limit exists if and only if both these one-sided limits exist and they're equal. If they're equal, then we simply say that this two-sided limit, or just the regular old limit, we say that that is equal to whatever that value is, in this case, 2. So these are called one-sided limits. Remember, when you see something like this, you should think the limit as x approaches 1 from the left of f of x. This is the limit as x approaches 1 from the right of f of x. And in this particular problem, both of these limits turned out to be 2. Now you might wonder, why do I need this complexity? Why can't we just say what this limit is and be done with it? And in the case of functions like polynomials, this is always going to be true. These functions are always going to exist. These limits are always going to exist, and they're going to be equal And this limit, this full double-sided limit, is always going to be the same as these two numbers. But the world isn't always made up of polynomials. There are more complicated functions where these limits, these one-sided limits, might actually be different. So let's look at one of those. Okay, here we have a nice piecewise functions. You guys are probably, you're either getting very tired of these functions or you're getting very good at these functions. Hopefully the latter, without too much of the former. So this is a great time to pause the video, graph this function on your own, and then come back to see how you did. I'll be right here waiting. Okay, great. That was fast. You're very good. Okay, here we go. Here's what I got when I graphed it. This part of the graph corresponds to x plus 2, x greater than or equal to 1, right? So when x is bigger than or equal to 1, I get this line. When x is less than 1, I get a parallel line with a different intercept, y equals x plus 1. That's down here. Okay, when x is less than 1, we get this line. I have to put an open dot here because this line only works when x is strictly less than 1. Here I put a solid dot because this line works when x is greater than or equal to 1. And a graph like this is pretty crucial to understanding what these limits are going to be. So let's write those down again. The limit as x approaches 1 from the left of f of x equals. Imagine walking along this part of the graph toward 1, right? We're coming close to 1, closer and closer to 1 from the left. What are my y values getting close to? They're getting close to 2. Okay, let's look at the right-hand side. The limit as x approaches 1 from the right of f of x equals. Now I'm approaching along this line, this part of the graph. What are my y values getting closer and closer to as I approach x equals 1? They're actually getting close to 3. So this is an example of a function where the left-hand limit at x equals 1 and the right-hand limit at x equals 1 do not match. They're different numbers. And what this essentially means for the graph is that there's going to be a gap. If I were to draw this, if I were to try to draw this graph all in one go, I couldn't do it, right? I draw this, I have to lift my pen or pencil or stylus and then continue on here. I can't do it all in one continuous stroke because these numbers are different. In this case, we say that the limit as x approaches 1, this is the double-sided or full limit, does not exist. These two limits can't agree on each other. This limit says 2, this limit says 3. That's never going to be the same. This limit does not exist. Let's look at some more examples where limits may or may not exist. Once again, here's a great time to pause this video, see if you can determine all three of these limits. The left-hand limit as x approaches 1, the right-hand limit as x approaches 1, and the full limit as x approaches 1. I'll be right here when you're ready. Okay, once again, you did that so quickly. Impressive. Here we go. Let's look at this one. And don't worry about what the function actually is. It doesn't really matter. Okay, as x approaches 1 from the left, my limit is 2. I won't write down the whole expression, but I'll put it in the same color. Okay, so that one's 2. The limit as x approaches from the right, well, that one is 3. Do these numbers agree? This one's 2, this one's 3. No, they do not. So our full limit does not exist. Okay, how about this one? Does it really matter that this one's an open dot, this one's an open dot, whereas this one's an open dot, this one's a solid dot? if you're getting good at limits, you're going to realize, wait, that doesn't change the limit whatsoever. And you're totally right. The answer to the 3 limits for this one is going to be exactly the same as this one. I'm just going to copy it right over. There we go. How about this graph? Okay, left-hand limit. As x approaches 1 from the left, it looks like we're going to get 2. As x approaches 1 from the right, it looks like we're going to get 3. Sorry, just kidding. Also 2. So what does that mean for the full limit? These numbers agree, and they exist. So the full limit is, in fact, 2. Okay, how about this one down here on the lower left? This is almost the same as this graph that we just did, except that there's a floating dot. Well, I'm hoping that you realize that, well, this floating dot does not really change anything when it comes to limits. The limits are going to be exactly the same as my graph right here. So I'm just going to copy those answers right there. Left-hand limit 2, right-hand limit 2. They both agree. The double-sided limit is 2. Okay, finally, a little bit of a different graph. In this case, the function goes off to infinity. And in a previous video, I said, well, that's not a number. Infinity is not a number. Limits have to be numbers. If they're going to exist, a limit has to be a number. So in this case, both the left-hand limit and the right-hand limit do not exist. So the full limit does not exist. So I guess I'm going to have to write that in all the colors, aren't I? Does not exist, does not exist, and does not exist. That's it for this video. I hope you enjoyed it, and I'll see you next time.